Welcome back, and let's start looking at how we can apply this idea of infrared spectroscopy. We've talked about how it can be used to identify functional groups. Let's see how it actually works. So as we went through before, the troughs in the graph are occurring at the wavelengths for which IR radiation is being absorbed. Okay, so here we have 100% transmittance, so all the infrared radiation is being through to the detector, and then here it is being absorbed in this part of the spectrum, okay, corresponding to the wave numbers, which corresponds to high energy or low energy. Okay, so we can see here that we have a peak at above 3000. Okay, we have a CH peak here, and then we have these ones here, which would be typically below our fingerprint region. So this is actually a spectrum of ethanol, which we see here. And we can see that in ethanol we have CH bonds, we have CC bonds, we have CO bonds, and OH bonds. So typically we would expect to see a lot of what we call alkyl stretches or CH stretches, and these come in the region of 3010 to 2850 wave numbers. And we can actually see that here at around 3000 we have these strong absorbances here which correspond to our CH stretch. You can see that it's not precisely at 2850 or precisely, it's just below 3000 here, which sits right within the middle of this region. So it's reasonable for us to assume that that is indeed what they are. This CO stretch here actually comes in around 1000. So this is usually buried in our fingerprint region, but it is a very characteristically strong absorbance. So it's often one that you can find. So if you think that you have an alcohol or you think that you have an ester, it's a good one to look for to back up your hypothesis that this is the functional group you have present. And then of course, if we do have an alcohol, we would expect to see an OH stretch up in the high 3000s, and indeed we do see that on this molecule here. So you can see that we can justify this structure with the spectrum. So let's have a look at something going a little bit along the lines of what we saw with aspirin. In this example, we have propanoic acid, of which of course is a carboxylic acid, and we have methyl ethanoate. Both of these have the same molecular formula. They're functional group isomers of each other, and they have the molecular formula of C3H6O2. So if I had the molecular formula, I wouldn't necessarily know which structure was the structure of the molecule that I was looking at. And one way we can tell them apart is to have a look at the infrared spectrum. We would expect to see a resonance for the C double bond O, which always come in at around 1700 wave numbers. But in the case of the carboxylic acid, at around 3000 wave numbers, we would expect to see an OH acid stretch. Now, these I'm getting from my memory. You, of course, will be looking them up in your data booklet, and they are listed in your data booklet for you to be able to reference. Okay, in the case of methyl ethanoate, I don't have the aldehyde stretch. So, sorry, not the aldehyde. I don't have this OH stretch. So I wouldn't have this 3000 centimeter to the -1 absorbance in my spectrum. I would still expect to see a 1700 centimeters to the -1 absorbance for my carbonyl or around that region, but I won't have the corresponding acid. And if we look at those spectra, that is exactly what we see. We have our alkyl CHs, which are in here, which are being obscured in this one here by this broad beard-like, we call this like a broad absorbance for the OH, and it kind of looks like a jaggedy beard, which indicates the OH here. The C double bond O here of our carbonyl and our carboxylic acid, and of course our fingerprint region. Then we have with methyl ethanoate, we still have this carbonyl region here at around 1700, but we have lost the broad absorbance up around 3000 due to the OHs, and our CH that was being obscured before by the OH stretch is now clear and visible in the spectrum. So if you have a look at this, we can clearly see that the spectra are different, and by referring to the references of what those absorbances show, we can clearly see that it is the acid that is missing in this one here, indicating that it would be the ester. So what we're looking to do, remembering this is a qualitative technique, we're looking for the presence or absence of. Okay, that's all we're looking to see. Does it have a peak at 1700? If so, then it must contain a C double bond O. Does it have a peak that is broad and ugly above 3000? If so, then it contains an OH acid group. These two in combination mean that the product will be a carboxylic acid. If it doesn't have that broad ugly peak, then it can't be an acid under any circumstances. It must be another type of molecule that contains a C double bond O, either a ketone or in this case an ester. So this is the way that we would describe it. We would say that the methyl ethanoate, the absorption just below 3000 wave numbers is due to the CH bond. In propanoic acid, the broad absorption band is from the carboxylic acid, and it ranges from 2700 to 3600 wave numbers. Okay, and the C double bond O stretch in propanoic acid produces a peak at a different wave number from the C double bond O stretch of the methyl ethanoate. These are different C double bond O's, so we would expect to see them at slightly different frequencies. Ketones are another one that we can look out for. They tend to be a little bit more jaggedy. Again, they're a little higher in ketones, and we just refer to the wave number range when we quote these that is given in our data booklet. When we increase the structural complexity, we increase the spectral complexity. So if we have a look at this, which is vanillin, okay, we can see we have an aromatic benzene, we have this methyl ether here, this methoxy group here, we have a hydroxyl, and we have the aldehyde. So here I have my C double bond O, and then I have a number of other CO stretches that are appearing in my fingerprint region, so it gets a little bit too hard to be able to pick them out individually. I can see the CH here, and mostly I'm going to see this, and these are my aromatics due to my benzene up here. And that's largely all I can pull out from this, and all you're really expected to be able to do. Hexyne, now we have no oxygens, we have no C double bond O. So the key thing that we would look for is like a triple bond C, a CH, and then a triple bond CH stretch. And again, the ones that you're expected to look for are in your data booklet. If they're not in your data booklet, you're not expected to know them. So we talked briefly about peak shape in the last video, and basically peak shape is just a way for us to describe them when we're defining what it is we're looking at in a spectrum. So most of them are narrow. We do see a couple of broad bands. These are particularly usually involving things like oxygen and hydrogen, where we have a large number of different combinations of vibrational modes. They all overlap over the top of each other, so we get a broader absorbance. We have said it's primarily to do with qualitative analysis, and the only application we ever really use it for is qualitative. It is possible to do a quantitative analysis by measuring the intensity of those peaks, but it's not something that's done commonly. It's usually done for the analysis of atmospheric gases and things that are particularly sensitive. So we will never be expected to do a quantitative analysis of IR within the scope of what we're doing. Okay, this is just showing you some more spectra. The more spectra you see, the more you get used to picking out the common patterns, and that's what we're looking for. If we look at the spectrum of ethanol, we can see we have this broad peak here that's sort of smooth like a tongue compared to the jaggedy beard-like absorbance we saw with a C double bond OH. And again, it's different, but it's in the same region and has a similar shape for the OH stretch that we see for propanol with this one here. So this is due to our OH alcohol. And then this one also would be the OH alcohol. And it is important when you talk about these to differentiate the OH alcohol from the OH acid absorbance that we have, because they do have different frequencies. These will be our CH stretches here. And of course, within this fingerprint region, we would expect to find a CO stretch as well. So looking now, we can see at the carboxylic acid versus the alkanol. Okay, if we have a look here, compound X and compound Y, we see this one here, we have a broad absorption, just like the previous ones that we saw, smooth above 3000. So I would expect that this is an OH alcohol absorbance, whereas over here it's a little bit lower down, right at 3000 rather than at around 3002, 3500. So, and it's a bit more jaggedy, so this would be the OH acid. Okay, broad peak again, but different in appearance and different in its absolute wave numbers. So if you have a look here, we usually take it from the base of the peak. This is around 3000, whereas this is clearly above 3000. So they do have a slightly different resonance. Okay, let's have a look at this example and then we'll wrap this up. So this is a IR spectrum. It's of an unidentified compound, and you need to be able to identify the functional groups present. We've been given the molecular formula, which always helps because we want to look for things where they have, do we have one oxygen? Do we have two oxygens? Are we going to be looking for functional groups such as ketones, or are we going to be potentially looking at acids or esters? We can't have an ester or a carboxylic acid functional group unless we have the two oxygens. So if we look at this and we would refer to our tables in our data book, hopefully what you would see is this one stands out. These are below our fingerprint region, and then we have this one, and these little guys here are the main ones that we look at. So if we look at this, we can see that there is a strong narrow band at around 1700 wave numbers. Hopefully you are starting to already see the pattern in this. This would indicate some kind of carbonyl. Okay, so we've got some kind of C double bond O, which is corresponding at 1700. Then we have this broad peak. If we take it down, it's around 3000, and it's a bit jaggedy. So if you remember, we were talking about this before, this is likely to be an OH acid, so the OH stretch of a carboxylic acid. Okay, so based on this, if I've got two carbons, one of them must have a carbonyl. I therefore have an OH acid. Here, now I have three hydrogens that I still need to play with. If I put that together, I can see now that based on this spectrum, that my molecule that I'm looking at is indeed ethanoic acid. So we have identified an unknown compound simply by looking at its infrared spectrum, if we know the molecular formula. And next up, we'll look at mass spectrometry, which allows us to work out the molar mass of a compound, which helps us work out that molecular formula in another way. Okay, so these are the textbook questions relevant to what we've just looked at. Remember, you cannot do these questions or this unit without your data booklet. You have to be referencing it. Don't try and do them without it. Have a bit of a practice, and we are going to do many different problem-solving activities of these when we get to them in class. So good luck, and I will see you in class.